We actually have 5 people here, but we have 4 of these. That's okay. Basically, you're supposed to convert, in the first case, 9 parts per million to parts per 100, which is percentage. In B, you're supposed to go from percent to parts per million, kind of like I did over here. C, parts per million to parts per billion, and actually I will come up with one more, and then everybody can go around and do one. So, just so you know, let's start. Natalie, you can do A. Billy, you're B. Okay, but do them all, right? But that I'm going to pull on you for sure for A and B. And Glenna, I'm going to ask you for C for sure, but do them all. Autumn, D for sure. And Taylor's working away. I don't have anything clever, so I'm just going to say for that, I guess it'd be E, sorry. For E, Taylor, and everybody, I'm just going to say convert 320 parts per million to percent. Clear as mud. Okay. So the first one, what do you think, Natalie, for the first one?
I have no idea.
I think, well, as I was working them, there's actually very much a pattern. So let's see if we can apply this pattern. So if you're going from, let's see what that's parts per million to percent. So parts per million to percent, actually, you're going to have a smaller number, and so you're going to actually divide by 10,000. No? Yes? For, let's see, 4.6, I don't know, 4 billion years or so. Hydrological cycle, I don't know, maybe 3 billion years. I'm not sure how long. But anyway, we have air masses that are cold and air masses that are warm. All that means is that an air mass is just a chunk of air. If it's cold, it's sat up over the polar regions and then moved. And it's warm, it's still set over probably the equator and then moved. In your house, do they say warm air rises or warm air sinks? Warm air rises. Yep, warm air rises. And there is something to be said for that. Do you guys remember the troposphere is actually, when we're walking around, it's a troposphere. It's actually got the thickest amount of air, but it's not very deep. It's thick, but it's not very deep, so it's densely populated with air particles. As we climb a mountain, it gets thinner and thinner. We'll talk about that. So one of the things within the troposphere, I don't know if you remember, clear back a few slides ago, is that actually the way the temperature goes is it gets cooler as you go up. So it's warmest here and coolest here. You guys told me warm air rises, so check this out. We actually usually have this sort of kind of nice, and the word is convection, we kind of have this nice warm air moving up. We kind of have this sort of thing going on. It's a pattern within the troposphere. Now, if you get in the stratosphere, then the temperature is backwards. But now what can happen actually is we can have basically, like this slide is showing you, cold air closest to the surface and then warm air over that. And if warm air rises and cold air sinks, you're like, dude, well, it's pretty stagnant. The word is stagnant. Okay, so when that happens, depending upon where it happens, it actually can set our cities up, because they're generators of pollution, for losing their mechanism to kind of refresh their air. So this is called a temperature inversion, and it creates issues for places like Beijing.
Is Beijing surrounded like mountains, like Salt Lake is?
China, right? I'm not sure. Yeah. Some mountainous, yeah. But kind of what you're saying is mountains do make a barrier for actually air then can't move where the mountain is. It can move this way, okay, with the mountain range, but it's kind of stuck there. And actually, mountains are natural things to kind of create these temperature inversions too. So, all right. Whew. Dun, dun, dun. Okay. So we do concern ourselves with cute little molecules. Now, I don't know about you, but I'm probably never going to see a molecule, just an individual molecule. We don't have microscopes that will do that. But we know that they're there because collectively they make things that we can tangibly hold on to. I just think that's so cool. That's all the slides talk about. For instance, if we look at water, the compound water, we know that we use the chemical formula to represent water, H2O, 2 hydrogens connected with 1 oxygen. So that's the symbolic, okay? It's weird to look at the periodic table, I didn't bring it, but all of those letters are symbols for the elements. So this is H2O is the symbol for water. We could consider it, think of it as a cute little molecule and the properties it would have. Then we can actually scale that up and think on the macroscopic level. That would be like this. What does it do collectively, those cute little water molecules? What do they do when they're ganged up? So we kind of have that going on in the back of our minds. Because in this part, in chapter 2, one of the things we're going to do is take a look at trying to visualize those molecules. What are they doing with each other? So here's a question for you. I didn't have it's not a your turn necessarily, but look at the, and hopefully you guys can tell color. We have a central black one and 2 red ones. What is that molecule, according to that key right there? Carbon dioxide. Yep. It's CO2. Yep. Carbon dioxide. So again, we make things seem so simple in chemistry textbooks sometimes, like we really can isolate, but we have to think of them as being isolated molecules interacting with other things. So we're going to talk about naming. Now your textbook talks about systematic names versus what we really call it. Like you guys told me that this is water. I agree. It's the compound water. But more systematic, it would be dihydrogen oxide. Dihydrogen oxide. Yep. There's like a funny thing that goes around and like oh, somebody died from dihydrogen oxide poisoning. Well, you can actually OD, or is it would be OD? I don't know, but you can actually get too much water and die. There was somebody who was trying to win like a Nintendo and drinking so much water quickly, and yeah, they didn't live to get the prize because they died. But anyway, so we're going to talk about kind of some just quick naming. Now, do you remember the other day we talked about classifying matter, and I said matter can either be a mixture or it can be a pure substance, and if it's a pure substance, it can be an element, or it can be a compound. CPD is compounds. And I told you there were 2 types of compounds. They're molecular and they were ionic. Okay? And we actually talked about ionic compounds. Now, do you remember what I said? If you're looking at the formula of a compound, how you can tell if it's ionic, you look for there's the letter M. Metal. You look for the metal. Look for the union label. And if there is a metal, then it's an ionic compound in general. I mention that because I want to talk about naming not ionic compounds, but molecular compounds. And actually, there's a slightly difference to them. So with these molecular compounds, you should see no metals in the formulas coming up here. But we have these prefixes. So 1 is mono. What do you think 2 is? Di. Yep. What about 3? Tri. I'm liking it. How about 4? Tetra. Yeah. Tet's the right idea. How about 5? Could be quint, but they're going to P. So, penta. Yep. Very good. How about 6? Hexa. Yes. Very good. Hexa. Hepta for 7. Octa for 8. How about 9? Where's the letter N? Nana for 9 and 10. Deca. Yep. So these are prefixes that we're going to see used with to tell you the number of atoms of that type of element that are present. Okay. So I said dihydrogen oxide. Okay. So dihydrogen oxide. In fact, you can get that in your notes. If actually you don't have to, because you're going to be doing a few examples to get your notes. So what we do, bless you, for molecular compounds, bless you. Now this is systematic naming, and we're not all, life isn't as clean as we'd like it to be sometimes. So systematically naming, we say how many atoms of each type of element there are, and then we end in IDE. Okay? So let's see what we think this one would be. So it's going to end in oxide. So what's the first name going to be? Dinitrogen oxide. And actually, I can see here, I didn't call it oxide, I called it monoxide. Or monoxide. Carbon monoxide. Dinitrogen, why did I call it or I didn't, but the textbook, why do we call it monoxide? Because it's just got one. That's cool. What about this one? Diphosphorus. Pentaoxide. Or notice it doesn't have the A. So it's just not pentaoxide, but pentoxide. I would take either one, but I don't know if Learn Smart would take either one. But so diphosphorus pentoxide. Perfect. Now it's your turn. So write the formulas for these and then give the names of these.
I think if it's the oxide at the end, if it just has one, then they put monoxide. But if it's at the beginning, like the B on sulfur, they don't put like monosulfur.
That sounds right to me too.
I think it's just that the second one has to be one.
Yeah, there's one. Yeah, that sounds right to me too. Okay, formulas. Natalie, what's the formula for the first one?
NO.
And it's yeah, it's exactly what I'm saying. Perfect. What's the formula, Billy, for the second one?
NO2.
NO2. I'm liking it. Glenna?
N2O.
N2O. Yep.
Yep.
Perfect. Autumn?
N2O4.
N2O4. I'm liking it. Taylor?
Sulfur dioxide.
Sulfur dioxide. Perfect. And back to you, Natalie.
Sulfur trioxide.
Sulfur trioxide. Any questions? All right, so this is one of the, let's see how to say this. That's so can you see where, as we go from the top to bottom, these are, what's the difference here? We're increasing in, yeah, increasing carbons and hydrogens, exactly. Now, I'm going to show some names over here, and not only are we increasing carbons and hydrogens, but it's a special family of compounds. It doesn't say it up there, but these are actually called, well, it says hydrocarbons. Okay, that's awesome, because sometimes we hear that word in the news, hydrocarbons. Makes sense. Only hydrogen and carbon all the way down. The other thing is these are very special. These are what we call entirely saturated. Have you ever heard of saturated oils or unsaturated oils? Well, in this case, these are all just all single bonds, and that'll make more sense later. And actually, as that turns out, and I can tell because of the number of hydrogens they got, and if they're all single bonds, these are equal to a family of hydrocarbons called alkanes. So I'm gonna go ahead and hand this out. This actually says kind of the different families of compounds you can have. They aren't all alkanes. Excuse me, they aren't all hydrocarbons. But if you find alkane here, it says RH, and the R is just a bunch of carbon and hydrogen, and the H is hydrogen. So I mention that because guess what alkanes end in? They end in A-N-E. So the way naming things like alkanes go is that we have a suffix on the end, A-N-E, and we have a prefix, in this case, to show you how many carbons they have. So it looks like this. And I tried to bold, M-E-T-H. M-E-T-H means one. A-N-E, alkane. Methane is one carbon alkane. And I tried to bold ETH here. So ETH means two. ANE means alkane. So here we have an ethane, two carbon alkane. I'd ask you for these, but you say three, like let's try. But for whatever reason, we go P-R-O-P. For three, P-R-O-P means three. The fact that it's an alkane means we end in A-N-E. So you've heard of propane before, so there you go. It's just basically carbon, carbon, carbon with hydrogens all the way around. That's propane. Now we get to, did we say, what is it? 4 before was tetra, right? Well, here it's bute, for whatever reason. So, yep, we've heard of butane before. Bute means 4, and the fact that I'm ending at A-N-E means it's an alkane. So it's a 4-carbon alkane. Well, here this is finally up to something kind of matches with what we were just talking about. P-E-N-T means 5. We're going to end it in A-N-E. So it's a pentane. It's an alkane hydrocarbon with 5 carbons.
So how come they're all not like that?
How come what?
They're not like
That the other list we took?
Yeah.
How come they aren't? I don't know. That's a good question. Historically, they're talking about they must have diverged somewhere. Because I agree. Because I agree. But you're right. So pent, hex, I mean, these others work. So a 6-carbon hydrocarbon alkane would be hexane. What about 7? Heptane, you're right. Again, the HEPT means 7, and the suffix ANE in this case is specific for alkane. How about 8 carbons? Octane. Da, da, da. We kind of hear that sort of referred to with regard to the fuel efficiency of our vehicles. How about 9? 9? 10? Decade. Again, I hope you guys see where these names that I listed on this table actually have a prefix, which is the number of carbons, and a suffix because they're alkanes. Oh, we're going to do a whole part today. And I don't have part 3 done yet, so we're not going any further. Okay? All right. So I never learned it. This first paragraph up here, mother eats peanut butter. Oh my gosh. So mother, methane, eats, ethane, peanut, propane, butter, butane. So that's your first, the meth, F, P, pro, B, bute. So I never learned it that way. So let's just kind of see these together. Now, notice that I have, you can see the F. So how many carbons does ethanol have? 2, right? But the all actually goes to, in general, an alcohol. In the sheet I gave you, if you find alcohols, you'll find the suffix OL, like ethanol, and you'll find the dash or the ROH. R means anything, carbon and hydrogen, but what's important about an alcohol is they have that dash OH. What about methylene chloride? Forget the chloride, but methylene, how many carbons are you talking? 1, exactly. Now, if you look on the sheet that I gave you, we have methylene. It ends in ENE. So can you see where we're looking at an alkene? And the sheet I gave you, what's different about it is you see a C double bond C, so that we do have double bonds here. So it's not an alkane, it's an alkene. How about propane? How many carbons? 3. Prop is 3. Yep, very good. And ane means it's an alkane again, where it's all single bonds, carbon and hydrogen. Very good. Okay. Thanks for playing along. And then tomorrow, like I said, bring your write-up and feel free to kind of sketch in your notebook if you want to before you come or as you come. And I think this is one of those labs that as long as you don't get crazy with the rulers or anything, you don't have to wear your goggles, your safety goggles for this one. Okay? So we'll come and do and go home. See you tomorrow.